Let us start module 1 lecture 21. This lecture is on effective current for near threshold voltage inverters. Now this is a continuation of the previous lecture. So we had begun an introduction for near threshold voltage inverter behavior and also the way these near threshold voltage inverters would behave in an inverter chain with balanced fan out ratio, all the stages having equal fan out ratio. We had discussed in the previous lecture that the current drive and the parasitic capacitance of an inverter would approximately increase with proportionally with device width or with number of fingers. In the standard cell scenario, the device width would be increasing as number of fingers, and in custom layout scenario it may increase as the width itself or as number of fingers. So, with both of these, the current drive and the parasitic capacitance and also this coupling capacitance between input and output in an inverter would increase proportionally. Now, we are interested in this discharge. This is the output discharge and this is the input. Now, what do we observe here? While the input is rising, at that time there is an overshoot in the output and the input rises till some point almost monically, but after that there is a period during which the input voltage would rise not to VDD. So, this VDD is also not VDD, this is VDD as we had discussed because of the leakage currents. So, when the input is VDD, there is a leakage current of the P MOSFET and I on by I off of the inverter is already not very large. So, therefore, we would find that this is not VDD, this value is VDD minus VDS of N MOSFET into I leakage of P MOSFET as we had discussed earlier, this value. So, this is like VDD static. Okay. Likewise, what is this value? Likewise, we can also discuss a VSS static, that is VSS because of leakage current of the P MOSFET. So, this would be, now there is a leakage current through the P MOSFET and that goes through this N MOSFET. N MOSFET is on because input is high and N MOSFET is on. So, therefore, there is a finite VDS and that comes out as in the output it looks like the 0. 0 is not this. So, its value we would find out as VDS of the N MOSFET when its VGS is 0. So, if you are able to, let us write it here, VSS static. So, what is this? In popular parlance we call it VOH or VIH. Now, this is likewise we can also estimate the same quantity for the 0 at the output. So, what is that? Let us do. So, let us call it VSS static, which is VDS of the N MOSFET as a function of I leakage of the P MOSFET. So, this one can call as VIL or VOL, whatever, depending on the context. So, what we observe is that the input has not risen fully to VDD during the output transition of the inverter and similarly we also observe that the output also does not reach 0 immediately. I mean it also has an intermediate value, it transitions at an intermediate value and then falls to 0. This is a special characteristic of near threshold voltage circuits or inverters. What is the overshoot due to? The overshoot is because when the input rises, input voltage rises, there is this coupling capacitance between input and output, which is essentially because of CGD of both the devices, and the N MOSFET is, in this case N MOSFET is off, P MOSFET its VDS is near VD at this point, and when the input rises because of the coupling capacitance, there is an increase in the output voltage and for a while the source and drain of the P MOSFET exchange each other. During the overshoot, the source becomes this overshoot and this becomes drain during the overshoot. In normal operation, the source and drain are again flipped and exchanged for the P MOSFET. So, and so there is a positive current from output to the VDD during the overshoot for a while. After that the N MOSFET is on in the sense in near threshold voltage regime there is nothing like on and off. The N MOSFET current is appreciable and it also discharges the output node. Now, as the input voltage increases, the N MOSFET current increases exponentially, not in a linear or square law manner as it happens in the nominal voltage regime. So, this exponential increase we would see that would cause a sudden increase in current. So, therefore, the current the N MOSFET discharging current is very large in this part of the input transition compared to what it is in this part of the input transition. So, there is an exponential increase in the N MOSFET discharging current from here till here. So, most of the discharge therefore takes place here. It would not take place in the lower part of the input transition. Whereas, in nominal voltage regime, if this is the threshold voltage, suppose 20% is typically the threshold voltage in nominal voltage regime, 20% of VDD. So, from here onwards, from 20% of VDD itself, there is a discharge of the output, appreciable discharge of the output taking place. So, the output voltage fall would happen at a lower value of input voltage in nominal voltage operation. Here it would happen for a quite a high large value of input voltage in the near threshold voltage operation. So, that is a difference and therefore, we would observe that this overshoot, now the overshoot for the nominal voltage regime would mostly happen when the MOSFET is not conducting. So, that would happen within 20% of the input transition. Whereas, here we observe that the overshoot, the increase in voltage in the overshoot keeps on happening till say it is the input voltage is 75% of VDD. The reason being the small current that N MOSFET would have here and it would exponentially increase and become appreciable only after around 75% of the input of VDD when input voltage reaches 75% of VDD. So, that is a difference that we see. So, in our previous discussion in one of the previous lectures, we had discussed that VDD and VSS in nominal voltage also VDD and VSS are not exactly, I mean the output values at the output and input terminals, they are not exactly VDD and VSS, that is because of the leakage current. Suppose the output is supposed to be 0, there is a leakage current in the P MOSFET and that would cause a finite VDS for the N MOSFET and therefore, V out is not exactly 0. Okay. And this becomes even more important in near threshold voltage regime because of the smaller ion by I off ratio as we had discussed earlier. So, we would find that VOL or VIL, the lower voltage, which we can also call VSS static, would be VDS of the N MOSFET for a current equal to leakage current of the P MOSFET. Now, we can calculate that because we know the R on of N MOSFET, we can always calculate this VDS. Okay. So, what and this is actually this value. So, this is what we had discussed earlier. We did not discuss this in any way. So, there is this value also which is important. Now, this is because of the coupling capacitance that we have indicated here, input and output coupling capacitance. So, what happens here? So, when the input rises, the output starts falling and once the output starts falling, now this is actually an inverter chain, I1, inverter I2, inverter I3. Suppose this is our inverter I2 that we are discussing. Okay. So, inverter I2 is our device under test. So, here when the input voltage is rising and the output voltage is falling, it is the P MOSFET of inverter I1 which is on and but its VDS is quite small. And here the N MOSFET of inverter I2 is on and its VDS, its VGS is quite, so it is conducting quite well. So, it would the coupling capacitance because of the small drive currents, the coupling capacitance causes a back coupling from the output to input and the input voltage itself is affected in the chain of inverters. So, now that is not equal to, if we similarly define VOH or VIH, which is VDD static, and we define it as VDD minus VDS of P MOSFET, which is a function of I leakage of N MOSFET. If we define it this way, so then this will be this value, but we are not discussing this. So, this VDD static would be this value, not this, for which the output discharge is happening. So, output discharging is happening for a VDD which is even smaller than the VDD static that we had discussed in the previous lectures. So, and likewise for the next stage, for I3, the output charging would happen for a VDD static for a value of VSS or 0, which is not VSS static, which is slightly higher than that. Now, this is in the PDK that we are discussing, which is 65 nanometer, which is a commercial foundry 65 nanometer planar PDK. For it, this turns out to be this transient input voltage during the output discharge turns out to be 0.95 VDD for our sizing of the inverter. In different PDKs, it may turn out to be a different value, especially in FDSOI or FinFET technologies. You would observe that it is actually much smaller than this. It could be even 0.8 or 0.75 VDD. So, therefore, this value is important. The output almost the entire output transition is happening because at this value of the VDD. So, the VDD that we actually consider for input voltage would be different, and for an inverter chain with balanced fan out ratio of at each stage, that is equal stage effort, because of the one-to-one input output correspondence that we had discussed in the previous lecture, we would find that this is a unique value. This VDD during transition is a unique value. Now, let us give this a name. Let us call this as VDD effective, and let us call this as VSS effective. This is not the actual VSS and VDD, but this is the value of input voltage. So, this is not the actual VDD, this is the input voltage that you would see. So, whenever you want to say that input voltage is VDD, it is actually this value, it is not VDD. You must replace it with VDD effective. You must extract this VDD effective. So, during the transition is equal to VDD effective. Now, this VDD effective is unique for a balanced inverter chain, and therefore, it can be extracted using simulations. Okay. So, now we will continue from this point. We will now divide the input transition and the output transition into several parts. As you can see here, we will, before the peak value, which we call VP, before the peak value, the transition before the peak value, the transition from peak value to 80% of the output reaches 80% of VDD. Now, why that? That we will discuss, and then from 80% of VDD to the time at which the output reaches 50% of VDD. So, we will divide our entire input and output transition into these three parts, obtain an effective current value for this inverter, and use that effective current value in obtaining an accurate value of logical effort of the inverter. Now, this effective current value and the logical effort would be in terms of the device level and layout level parameters. So, we can account for variations in the logical effort value for an inverter operating in near threshold voltage regime. Now, this is important because the variations play a more significant role in near threshold voltage regime compared to what the role that they have in nominal voltage regime. So, as we had discussed, because of the coupling between the input and output nodes, there is a voltage that you see during the transition. This is the input transition, this is output transition. So, during the output transition, the effective value of the gate voltage that you see, gate voltage V in that you see is smaller than VDD. In fact, it is smaller than VDD static that we had discussed. So, it is even smaller than that. So, in the 65 nanometer PDK that we are always referring to, it is, we find it to be 0.95 VDD for balanced input and output, balanced inverter chain. And this could be different in different technologies. In typically in FDSOI or FinFET technologies, it would come out to be much smaller. That we will discuss later. So, now why is it unique value in inverter chain that we had discussed? So, it is because there is a one-to-one correspondence for a balanced inverter chain. That is, if the inverter chain has a constant stage ratio throughout, there is a one-to-one correspondence between the input and output, and therefore, you would always have constant value of the input voltage, constant value of the input voltage while the transition is happening. That is, when you change the stage ratio from fan out 3 to say fan out 5, what you would find is that this transition time would increase, this transition time would increase, and this would also increase for the same while. Suppose it is 0.95 volts VDD, 0.95 VDD from here till here. Between these values, again for the increased transition time between these values, you will have again 0.95 VDD as the input voltage. That is what we mean to say, that for balanced inverter chain, balanced fan out inverter chain, you would have this VDD effective also being unique. So, when the input rises till the time the NMOS current, discharging current, input is rising, the NMOS discharging current, till the time it is negligible, what we find is that because of the coupling capacitance Cm, the rise in input would also lead to a rise in the output voltage. That is because for a positive charge to get collected at the input node of the coupling capacitance, there must be a corresponding negative charge which is getting collected at the output terminal of the coupling capacitance Cm, and with this being node connected almost through high resistance paths, you would have, for the negative charge to get collected here at this output capacitance, a balanced positive charge has to get collected, and that leads to an increase in the voltage. Physically, that is how we can explain it. So, there is an overshoot here, and this overshoot is, we consider this in deriving the timing expressions. And so, after this what happens is the output falls, as is obvious once the NMOS current starts becoming significant. So, what is the behavior of current? So, initially when the input voltage rises, initially we find that there is almost a linear increase in the current. That is because gate voltage is increasing, and with gate voltage we would find that the current I out, which is approximately equal to the NMOS current, can be simply written as V in minus VTH plus lambda VDS by NVT. This is thermal voltage VT, VTH is the threshold voltage of the NMOS, let us call it VTHN. Now, what is the value of this VDS? We find that in this region, when the input is rising, most of the time the value of VDS is almost near VDD. Even when you change the fan out ratio, you are keeping the inverter chain balanced, that is, you are keeping the fan out ratio constant in all the stages. So, therefore, there is a one-to-one correspondence between input and output transitions, input and output voltages. So, we find that during the input transition, if it is near VDD, the value of output voltage for a given fan out, say fan out 3, for fan out 5 also, it would remain the same within the input transition. So, therefore, we can safely take this value of VDS as VDD. So, that is what we do. And so, this is an exponential increase with V in, but when we look at a small section of an exponential increase, it would look like a linear increase. So, we find that this is a linear increase, approximately it is a linear increase in current, and from what value to what value? We are saying that from Vp, that is peak voltage of the output overshoot at the output, that peak voltage to 80% of VDD. Why we take peak voltage to 80%, that we will discuss as we go ahead. So, till this 80% of VDD, we find that the input transition is not complete, that is the reason, and therefore, we find that the output current from which is discharging this output node, the output current which is discharging this output node is almost increasing linearly. Okay. And you would say, why should we take it to be linear always? See, we are maintaining the stage ratio in our example. So, here the stage ratio is balanced, the stage ratio can increase, but it is balanced. So, say it is fan out 2, then it is fan out 2 for all the inverters. If it is fan out 5, then it is fan out 5 for all the inverters. That is what we mean by balanced stage ratio. So, when you increase the stage ratio, you are increasing the current to capacitance ratio at every node. The supply current is increasing because you are increasing the stage ratio. So, second inverter increases from say fan out, suppose it increases from fan out 3 to fan out 6, then the size of the second inverter increases by 2 times. The size of the third inverter would increase by 4 times. The size of the third inverter would increase by 4 times. So, what would we see? We would see that the current to capacitance ratio for between the third inverter and the second inverter would remain the same. So, that is why we would find that the current drive, increase in current drive would be similar, in the sense that if the transition time now increases by 2 times, the current also increases by 2 times. The current drive would increase by the same ratio as the stage ratio. So, but the nature of current, increase in current would remain the same, because the terminal voltages, there is a one-to-one correspondence between the input and output terminal voltages, that we had discussed earlier. So, when there is a one-to-one correspondence between input and output terminal voltages, the corresponding current, terminal current would also increase only because of the size of the gate. Its nature would not change, because terminal voltages are the same. So, you will find the same nature of the current, only its value would increase proportional to the size of the gate, that is all. So, that is why we would find for all the inverter chain cases that we are considering, that if there is a linear increase for one stage ratio, you will find a linear increase for all the stage ratios between when the input transition is happening. After the input transition happens, what should we consider? That we will discuss after this. So, there is a linear increase in the current from what we call V in C to V in equal to VDD into 0.8. So, what is this V in C? V in C is the voltage of input when the output overshoot attains its peak value, that is the corresponding input value, input voltage, and that is unique again, because when you increase the stage ratio in a balanced inverter chain, you would find that because there is a one-to-one correspondence between the input and output voltages. So, it is again a unique value, and V in C is also a unique value. So, this is the input value corresponding to the peak at the output. Okay. So, we are finding that between these two there is a linear increase in current, and it is a small section of an exponential actually, otherwise this is an exponential relationship. So, what happens after the input reaches 80% value, the output reaches 80% value, the output has fallen to 0.8 VDD. We want to calculate the time till output falls to VDD by 2. Okay. So, once it reaches 0.8 VDD, we find that nearly the input has saturated. So, if the input has nearly saturated, this is again for different fan out ratios, this would again saturate in the same way because of the one-to-one correspondence between input and output voltages. Okay. So, it would again the input would saturate when the output reaches 80% VDD for any stage ratio in this PDK and for this PN ratio, WP by WN. Okay. So, as a side note, we can say that for given PDK and WP by WN ratio, one-to-one correspondence between V in and V out. Okay. This ensures, what does this ensures? That the nature or the important voltages, that is Vp to V in C and V out equal to 0.8 VDD to I out correspondence remains same for different stage FOs. Okay. So, if you change the FO of each stage, fan out of each stage, you would find that this and this remain the same. That is, at 0.8 VDD you get the same I out. Okay. Same I out in the sense the transition of this I out. So, if the inverter size is increased, I out would proportionally increase, but you can predict the value of I out for a from the earlier value. That is, you had FO2. So, the inverter of a certain stage, the third stage had certain size, you had a certain value of I out. Now, for FO4, for this 0.8 VDD at the output, you would get the value of I out, which is proportional to the new size of stage 3 inverter, that is all. So that is what we mean to say here. So, from 0.8 VDD to 0.5 VDD, suppose this is 0.5 VDD. Okay. So, 0.8 VDD to 0.5 VDD, what is happening? Now, the output is falling, input has become constant. So, the V in is constant at 0.95 VDD. Okay. V out is falling rapidly. So, in the expression I n equal to I out, you find that this is V in minus V T H n lambda V out. So, we are discussing the values in this vicinity of V in. So, V in is only slowly rising here. So, V in, so we are here we find that V in is slowly rising and V out is rapidly falling. Okay. So, what would happen? So, you will find that this is the current becomes more or less constant. So, that is why you find almost a constant current in this region, okay, till the time output falls to 0.5 VDD. From 0.8 VDD, you find that the current is almost constant. It slightly reduces, but it is almost constant. Okay. Slightly it remains constant and then slightly reduces. After the value of V in has reached a constant value, it starts reducing a bit, but it is almost constant. So, what is the strategy then which we take up? We say that from V in being Vp highest value to 0.8 VDD, we take an average current of these two as the discharging current, and from V out being 0.8 VDD to V out being 0.5 VDD, we take this constant current as the discharging current. Okay. That is how we can estimate the delay or the time duration between peak and 0.5 VDD. What about 0.5 VDD at the input and between 0.5 VDD at the input and V in C? So, V in C is the value corresponding to Vp here. So, what about that? That we will separately estimate. So, then we add up all the time durations from 0.5 VDD at the input to 0.5 VDD at the output, and that gives us the value of the delay. So, for this we would require the value of V in C, that we are calling whatever we are calling V in C, that is when the output voltage is Vp, the corresponding input voltage is V in C. So, we will find the value of V in C first. So, for this we write the KCL at the output node. To obtain the value of V in C, we write KCL at the output node. So, now there is a coupling capacitance Cm dV in by dt. So, what is this? If the input is rising linearly, it is Cm VDD by Tr. Okay. So, that is the current coming in to the output node, that is the current coming into the output node, and what is that equal to? That is equal to the current going out of the output node. Out of the output node, we are neglecting the PMOS current here, and that is justified. So, what we find is that once the input rises slightly, there is an exponential reduction in the current which the PMOSFET can carry, because its gate to source to gate voltage or gate to source voltage is reducing in magnitude, and therefore, its current exponentially reduces, current drive capability. So, it is only the N MOSFET current which becomes significant. So, it is current coming in, output current plus the current charging the output capacitance, total output capacitance other than the coupling capacitance. Now, we are looking at this peak. So, here what is the value of dV out by dt? That is 0. So, therefore, this has a 0 value now. So, what is the value of this? Now, this is just I naught exponential V in C minus VTHN plus lambda VDD, because we are considering that V out is nearly VDD at this point, because the change in V out from VDD would be a small value, and anyway it is being multiplied by lambda, which is smaller than 1, right. So, now what is this? This we can rewrite as Cm VDD by T I naught TR as being equal to. So, now what can we simplify it further? So, let us try to get some sense out of this. We know that we have a balanced inverter chain. So, balanced inverter chain means what? We have all the fan out ratios same in all the stages. So, the input and output transition times are also matching, especially near V in equal to 0.5 VDD or V out equal to 0.5 VDD. We have input and output transition times matching output transition time. Okay. Because it is a balanced inverter chain, we would find that the input and output transition times match. So, especially in the vicinity of this 0.5 VDD at input and output. So, at 0.5, when the input is at 0.5 VDD, what is the input transition time? dV in by dt at V in equal to 0.5 VDD, and this should be equal to dV out by dt at V out equal to 0.5 VDD, which is this value. Okay. So, now what is dV in by dt at this value? Since it is it would be, if the input transition time is TR, then this would be VDD by TR, that is the rise time, and that is equal to the output transition time at 50% VDD. At 50% VDD, what is the output transition time? So, it is I out by CL at V out equal to 0.5 VDD. At V out 0.5 VDD, what is the value of input voltage? In our case 0.95 VDD. Okay. For every PDK we can just extract it out for a certain fan out for the inverter. It would remain the same for other fan outs in the inverter chain. So, it is 0.95 VDD, and what is the value of output voltage? 0.5 VDD. So, what is the value of body voltage? It is an inverter, it is 0. So, what is this? This would be I naught exponential V in, which is 0.95 VDD minus VTHN plus lambda V out, which is 0.5 VDD in VT. So, this is the value divided by CL. So, where do we use it? So, we had this expression V in C, from the expression where we related Cm VDD by TR to the current, that is KCL at the output node. From there we have V in C is equal to VTHN plus lambda VDD minus lambda VDD plus NVT, natural logarithm of Cm by I naught VDD by TR. This we are obtaining from the KCL at the output, which we have just solved. So, what is the value of this? This would be, if we substitute this value of VDD by TR, instead of VDD by TR, we substitute this. Then what do we obtain? 0.95 VDD minus lambda by 2 VDD minus N VT, natural logarithm of CL by Cm. What have we done? We have, instead of VDD by TR, we have substituted this and opened the natural logarithm. So, then we get this, and some terms like VTHN etc. get cancelled, and That is how it results into this. So, we have found the value for V in C. How do we obtain the value of effective current? So, that would be the topic of the next lecture. Okay. So, in this lecture we have discussed the value of input voltage which corresponds to the peak value at the output voltage. We also discussed our strategy to obtain the delay of an inverter in a balanced inverter chain. This we will be using in a variability aware sizing methodology for near threshold combinational circuits. Thank you.